recording now?
Yes, it is.
And let's see if it gets back in focus. All right. Welcome back to Math341, Lecture 6. What I want to do today is talk about the first talk in mathematical modeling, not the second one. And so the idea is to give you some sense of where this material is going and motivate why we're going to be spending so much time developing certain theorems, developing certain approaches. So I'm going to quickly review some probability. Some of this you may not have seen before. Some of you I know have already taken other stats classes. This is one of the challenges that you do not have the same background. That's fine. We will cover this up in greater detail later. I'm going to introduce you to difference equations. Difference equations are discrete versions of differential equations. One of the most famous is Newton's law, F equals ma. We use these all the time. I will talk a little bit about how to solve difference equations. And I'll talk a little bit about how to use this for modeling as to why these are the difference equations we want to study. How many of you have played roulette? I will give you a strategy that seems ideal to making a fortune at roulette. Given the fact that I am not in Vegas and I am here right now, you can imagine there is probably some subtle flaw with that strategy. All right, so background. So we've talked a little bit about probability distributions. They are non-negative. They integrate to 1, so I'm doing things that are continuous. And then the probability I take on a value between A and B is just the area under the curve from A to B. This is one of the reasons why we love calculus. Calculus allows us to calculate these probabilities. That's why we care about these areas. The mean, anybody who has been in a competitive environment knows what the mean is. It's the average value. So we would just take x multiplied by the probability it happens. The variance is how spread out it is. So it's x minus the mean squared. So if every value was the same, everything was always the mean, then the variance would be 0. And the more spread out things are, the greater the variance. One of my friends was a student at Harvard, and I remember visiting her, and they had the grades for a physics exam posted outside. So not only did the professor give the mean and the variance, he actually gave the third and the fourth moments of the distribution, so the grade-conscious Harvard students could really know how they sat relative to everyone else in the class. For most purposes, mean and variance is more than enough. We say two random variables are independent if knowledge of one has no impact on the other. You've got to be very careful that sometimes things might actually be dependent. If you are rolling die and you look at two different rolls, it might matter how you pick things up. Or if you're tossing a coin twice, do you pick it up heads or tails? If you flip the same way. Some people practice so that they can always toss the coin the same way. It is a very useful skill to get. One of the most important distributions, which we'll see throughout the semester, is the normal, the Gaussian, the bell curve. When you have this many names, you are important. So it's an exponential, either the negative x minus mean squared over 2 sigma squared divided by square root of 2 pi sigma squared. So you always want to think about units. So the mean has the same units as our random variable x. The variance has units squared, so it's the square root that's going to tell us the correct scale for fluctuations. And the big theorem that we'll prove mostly later in the semester is the central limit theorem. If you have a bunch of independent, identically distributed random variables, and you can weaken that a bit, and you look at their sum, then their sum becomes normally distributed. And so the right quantity that you often study is you look at their sum. Each one has an average value of mu, so if I have n of them, I would expect the average value to be n times the mean. And then sigma square root of n is just the right thing to divide by, so that in the limit, this converges not just to any normal, but to a normal with mean 0 and variance 1. Think of it as I'm always renormalizing things. So how tall is the average person? Well, it would be one thing in feet. It would be another thing in meters. I could just create a new unit, the average Joe. And the average person is one average Joe. Okay? Let's see how good this theorem does in practice. So it says that, as we take more and more random variables and we look at their sum, the sum becomes normally distributed. So here is a uniform random variable, and I've chosen it so that it has mean 0 and variance 1, and I've drawn the best fit Gaussian. Do you think this does a really good job? No. Right? And so the area under this curve is just 1. The area under the other one is 1. They don't look great. Do they look terrible? It's not terrible, but it's not a great job. This is the sum of two uniform random variables. What kind of shape is this? Triangle. Where have you seen a triangle before as the sum of two independent random variables? I'm sorry?
Last class, the triangle handler was the addition.
I don't think the last class. I'm thinking more from board games. If you roll 2 die, how many ways are there to get either a 2 or a 12? There's only one way. How many ways are there to get a 3 or an 11? 2 ways. A 4 or a 10? 4 ways. All the way up to a 7, which has 6 ways. So if you look at rolling 2 die and you look at their sum, the sum is going to be a discrete sum of 2 uniform random variables. And you can begin to see, yeah, that triangle, that matches by intuition. So whenever possible, you always want to recast things in terms of something you've seen before, something you know. Where have we seen sums of uniform random variables? Rolling die. All right. Now that we've done 1 and 2 sums, what should we do next? You would say 3, but 3 is wrong. We skip 3 and go straight up to 4. Why 4? Grouping in parentheses. If I know the distribution of x1 plus x2, then I just take that distribution twice and I add it to itself. It's often easy to work with perfect powers of 2. Now it's getting to be a pretty good fit, and with 8 it's going to be an exceptionally good fit. If you want, you can write down explicitly what the density function would be for sum of 4 uniform random variables. If this excites you, you need help. The department will provide it. Okay? You should not want to work with something like this. Saying, hey, look, it's approximately a Gaussian, and the Gaussian has a nice density. Let me work with the Gaussian, and then just have some control over the error. This is one of the big themes of the class. This is only sums of 4, and this is the nice case of sums of 4 uniform. Try to imagine what it would be like if you wanted to do 8. If this excites you, try to do 8. And that should cure you of it. Okay? This is why we prove these great theorems. This is why we prove the limiting behavior. It's much easier to work with those distributions than to work with these piecewise definitions. All right. Introduction to difference equations. So again, as I said, it's a discrete version of differential equations. I'm assuming my nth term in the sequence is a function of the previous L terms. For some more complicated problems, it could actually be a function of every term, going all the way back to the beginning, so that the number of terms that matter is actually growing as you go further and further down. This has only finite memory. That all that really matters is what were your last L states, and then from that point onward, it's independent of how you got there. So the Fibonacci's, Fn is Fn minus 1 plus Fn minus 2. It's each number is the sum of the two previous. And normally we start, 0, 1, or maybe we start 1, 2. So we say something is a constant coefficient fixed depth if I have a relationship like this where the C's are fixed and I always go back exactly L. These are the easiest ones to analyze. And it turns out they model a lot of problems. So the goal of this class is to develop a theory to allow you to model things and understand what's happening. So we can compute, but it's expensive. So if I wanted to calculate the millionth Fibonacci number, I could just keep iterating and marching down. So one of the themes is how do you do things quickly and efficiently? So linear algebra was supposed to be a prerequisite. I want to actually show you that linear algebra is good for things. Just in case you left linear algebra without an understanding or appreciation of its power, it's worth taking a little bit of time and saying, well, we've got a prereq for the course. Why don't we use that prereq? So I'm going to write the Fibonacci relation in matrix form. Fn plus 1, when I multiply, will be Fn plus Fn minus 1, and then Fn will just be Fn. And so what I can then do is it leads to the matrix formulation. If Vn plus 1 is this, and Vn is that, and my matrix A is that, I get Vn plus 1 is A Vn, or A squared Vn minus 1, all the way down to A to the n V1. And sometimes people have trouble, well, how many powers of A do I need to get back at the end? Well, A to the first plus n is n plus 1, A squared plus n minus 1 is n plus 1. These are supposed to sum to n plus 1, so I know this has to be an n if that's a 1. And now we can use linear algebra. We have a matrix. This matrix can be diagonalized. And because it can be diagonalized, we then can write our vector in terms of some linear combination of the eigenvectors, the u's, the lambdas, and the coefficients. So for the Fibonacci numbers, we get one of my favorite formulas in all of mathematics, Binet's formula. The nth Fibonacci number here is an explicit formula for it. Anybody know approximately how large 1 plus root 5 over 2 is? Approximately. Yes. 1.6, also known as greater than 1. This number here is less than 1 in absolute value. So as n gets very, very large, this number goes to 0. So what this tells you is the nth Fibonacci number is actually whatever integer is closest to this part right here. This allows you to calculate Fibonacci numbers very quickly. Does this look like an integer? No. I always like to say if a number has mugged you and the police round up some suspects and there's a lineup and you ask to identify, you would not point to this as an integer. But miraculously, all the algebra works out. So as a nice exercise, what can you replace the 5s and 2s by so there will always be an integer? Right. How many of you have seen Star Trek 4? Okay. Somebody incorrectly recently stated that Star Trek 4 was the best of the Star Trek movies. What's the best of the Star Trek movies? That's even worse than saying Star Trek 4, because that's saying Star Trek 5 is as good as Star Trek 2. Star Trek 2 is by far the best. But in Star Trek 4, it's very complicated, but in order to save humanity in the future, we have to travel back in time and bring forward 2 humpback whales to repopulate the species. Humanity depends upon this. So we're going to use this as inspiration for the following problem of trying to model real populations. So I am going to make several unreasonable assumptions. That's fine. This is meant to be an initial toy model. Does your initial toy model have to capture all the features? No. If you then try to apply your toy model to the real world, should you? I'd be concerned. You want to try to then slowly introduce more features, more complications, and see if you can still handle it. But if you can't even solve the toy model, good luck with the more general complicated one. So in the toy model, I will assume the wheels always die when they turn 4, and they never die earlier. Do you think this is reasonable that all wheels die at the same time? Okay, good. Nobody thinks that's reasonable. I will assume that each pair of wheels become pregnant when they turn 1 and give birth to 2 pairs when they turn 2. So you get 1 child or 1 pair of children when you're 1, 2 pairs of children when you're 2, and you always do that. Oh, I'm sorry, you give birth to 2 when you are 2, and you give birth to 1 when you turn 3. Okay. So instead of talking about male and female wheels, I'm going to just talk about pairs of wheels. So if I have 1 wheel, that means a real pair. Okay? And so now, can we figure out how many wheels there are of each age? So the answer is yes. It's completely deterministic. I tell you, if a wheel exists, the wheel will give birth to so many wheels when it's 1, so many wheels when it's 2, so many wheels when it's 3, and then it will die. One of the years it'll give birth to none, one of the years it'll give birth to 1, one of the years it'll give birth to 2. You can just go through and, similar to the Fibonacci, solve this. Well, that means we can turn it into a recurrence relation. Let's let AN be the number of wheels born in year N, BN, the number of wheels that are 1 year old, CN the number of wheels that were 2 years old, and D the number of wheels that were 3 years old in year N. Can anybody tell me what DN plus 1 would be? How many wheels are 3 years old in year N plus 1? What would DN plus 1 be? It would just be CN. Nobody dies until they become 4. So the number of wheels that are 3 years old in year N plus 1 is how many wheels were 2 years in year N. How many wheels are 2 years old in year N plus 1? It's however many wheels were 1 year old in the previous. And so you get the following recurrence relation. DN plus 1 is CN, CN plus 1 is BN, BN plus 1 is AN plus 1 is 2BN plus 1 CN. I can write this in a more expanded format and say, here's my A's, B's, C's, and D's. Or I can write it in vector matrix form. Here's my vector, what's going on in the N plus first year. And so I can just solve this similar to the Fibonacci's. I have a matrix. I want to calculate the eigenvalues. I want to calculate the eigenvectors. So these are called Leslie matrices. Does everybody agree that this model is unreasonable? Okay. So what properties does A have? Is this form reasonable? If you just go through, here's the mathematical code. It will compute everything for you. It solves everything deterministically. But what are some of the problems with this model? So somebody give me an issue. Yes?
The wheels don't all die before.
Yeah, wheels don't all die at 4. So maybe what we should do is we should have some probability of the wheels dying at each year. Maybe with a high probability you survive your first year, with a high probability you survive your second year, with a high probability you survive your third year, and then maybe the probability starts getting very small that you become a very old wheel. Okay, so that's one issue with the model. What's another issue?
Whales don't always come in pairs. Nicely neatly like you said they do.
Yeah, I don't want to remove that assumption right now, but yes, that is definitely an assumption.
So every whale gives birth to the same number of pairs
Yes.
the same year?
Yes. If you are not willing to give birth, then the whale council will get on your back. So that is another unreasonable assumption. So what you can do is let's try to modify things. So we're not always going to live to 4. We're not going to give birth to exactly 2 pairs and exactly 1 pair. Another issue is, of course, that we're assuming that there's infinite resources, that the whales will have an unlimited food supply. All right? We'll leave that assumption for now as well. But now here's the solution. We can put in random variables. And at a given moment of time, we can put in what is the probability of having this many pairs? Or what's the probability that you survive and move on to the next? Now what's very complicated about this is these numbers are going to be drawn from, say, a probability distribution. It's not going to be the same matrix every single time. So you can't just use the powers of eigenvalues to say, oh, I have a to the n, let me diagonalize a, and then I just take the eigenvalues to the nth power. You lose that ability. But you can model this very well on a computer. So just to introduce some notation for the class, yes?
How did you know where to plug in the random variables?
Well, if you go back to the matrix we had, these were the only non-zero places. So if I'm looking at how many wheels there were who are 3 years old, it's coming from how many wheels were 2 years old the previous year.
Right,
Nothing else can come in.
But all the entries were based on your assumptions. And if we're saying the assumptions are kind of wacky, wouldn't you want to put random variables in other places?
Well, but you can't have a wheel, you're not going to have a wheel do time travel and go from being 1 year and then growing 2 years while every other wheel grows just 1 year. So if you look at the transitions, if you're going to be a wheel who's 3 years old, you came from a wheel 1 year earlier that was 2. The wheels that were only 1 year old, they can't become a 3-year-old wheel in 1 year. They need 2 years to age. So that's why when I'm trying to generalize, these are the only places I can put things in. Now you could, and then these are all coming in from the possible reproducing. So these are the only cells that have a chance to have entries. Yes?
So the probability of survival, they vary from year to year.
It would vary from year to year. What would you tell me, can you give me any bounds on these S's? Your survival probability.
0.
Yeah, 0 to 1. You should not have a greater than 100% chance of survival, and you should not have a negative survival rate. So you can make the model more realistic. We typically use capital letters for random variables and lowercase letters for the values of the random variables. So this is just introducing notation that we're going to be using throughout the semester. So I'll use R's for the birth rates, and I'll use S's for the survival rates. And then it's going to look a mess like this, where I'll have different draws of the random variables. And unfortunately, most models can't be solved exactly. It's wonderful when you have a closed form solution where if I change this parameter by 5%, I can see what happens to my model. Typically, you can't do that. You have to resort to simulations. This is one of the dangers in academic classes, is we sometimes get so enraptured with beautiful theories that have no applicability in the real world because the real world is far too complicated. When my father was getting his master's in business, he took a class from a very theoretical professor who gave them an equation with 46 variables to determine what their company should do in various situations. And my father said, I don't even know the values of these variables for my own company, let alone for the competition. And she just couldn't understand why he wasn't enraptured as she was with this formula. It's got to be something that you can use. If you can do a simple model, and if it can capture enough of the features of the problem to be useful, that's great, go for it. Fortunately, most functions, while they can't be integrated in closed form, they can often be approximated with functions that can be integrated in closed form. So I was visiting Stat365 yesterday, and I saw a review of the standard continuous probability densities, and we will get to those later in the semester. Fortunately, they can model a lot of things in the real world. and then we have a chance of getting closed form solutions. And it's wonderful to say, well, if we increase all the survival rates by 3%, how is that going to affect the real population? All right. Now, we have products of matrices here. Products of matrices can become complicated. This is another one of my favorite formulas. I thought I would just introduce this. So we define square brackets AB as AB minus BA, the commutator of AB. If the matrices commute, if order doesn't matter, then the commutator would be 0. Can somebody give me a matrix that commutes with A? A inverse, A to any power, the identity matrix. 3A. But in general, two matrices do not commute. You should have all seen the exponential function here. E to the x is the sum of x to the n over n factorial. You can actually define a matrix exponential. All you do is instead of putting in a real number, you put in a matrix. And all of these, if A is a square matrix, they'll all be square matrices of the same size. You can talk about a matrix exponential. And then if you want to look at, what is e to the a plus b, your natural guess is, oh, it'll just be e to the a, e to the b. No, there's actually a term involving the commutator. Actually, there's infinitely many terms involving the commutator, involving commutators of commutators. There's a lot of problems. Any physicists here, or people taking advanced physics classes? All right. So sometimes you'll look at these unitary matrices and time evolutions of systems, and you'll have matrices like this. And unfortunately, when you have matrices that don't commute, the matrix exponential becomes very bad. But there are often closed form solutions in terms of matrix exponentials. It's just nice to be aware of how bad things can get. All right. Let's talk a little bit about efficient computation. So we found Binet's formula by using linear algebra. There's a lot of different ways to do it. One of my favorite ways is the method of divine inspiration. I don't know if I've talked about that yet in this class. This is where you are inspired and you write down the correct answer. You cannot always count on being inspired, especially on exams. But for a lot of problems, it doesn't matter how you get the answer. If you just write it down and check, that's fine. If I give you a huge number to factor, it may be very hard to factor, but it's very easy to check and see if your answer is correct. So a lot of times divine inspiration is fine, but it's fickle and it doesn't really generalize. So I want to talk to you about another way to find Binet's formula. And the Fibonacci numbers are not directly related to roulette, but a very close cousin of the Fibonacci numbers is related to roulette and trying to model something like that. All right, so first, let's look at this recurrence relation. Each number is the sum of the previous two. Well, because my sequence is growing, I get fn is less than twice fn minus 1, and it's at least as large as twice of fn minus 2. So what this means is the Fibonacci numbers are growing slower than 2 to the n and faster than square root of 2 to the n. Because every time I increase n by 2, I at least double my Fibonacci number. Every time I increase n by 1, I no more than double my Fibonacci number. We know the Fibonacci numbers are growing exponentially fast. So this suggests, why don't we try maybe the nth Fibonacci number is r to the n. All right? Well, if we try that, we will eventually be led to Binet's formula. So I'm going to show you a more formal way to get this using generating functions. Did you guys have on your first homework assignment 1 divided by 99,000? Right, and you all saw some strange thing. What was the big thing you saw when you did the division? What pattern did you notice? Fibonacci's. So I did not just randomly try a bunch of divisions until I found one. I didn't take a long string of Fibonacci numbers and then try to find a rational approximation. This is related to generating functions. This is one of the most powerful methods we have for tackling problems in mathematics. And it works as follows. Once I write down the Fibonacci recurrence relation, the initial conditions, say f0 is 0, f1 is 1, the Fibonacci numbers are completely determined. It may take a lot of computation to get them, but they are determined. So what I'm going to do is I'm going to build a function. G of x is the sum of fn x to the n. The idea is this is local information, and I get some kind of global object. And then the idea is to use information about that global object to then gain information back about the local objects. This only works if we have an explicit formula for the sum. I'm starting my sum at 1 because the 0th Fibonacci number is 0. How many of you have taken differential equations? Not that many, but if you've taken differential equations, you might remember series expansions and that technique. This is very similar to the series expansion technique. So what I'm going to do is let's look at n greater than or equal to 2 of fn plus 1 xn plus 1. I'm writing it like this because I can now use my recurrence relation to replace fn plus 1 with fn plus fn minus 1. Okay, well, I'm going to just shift some indices around. So this is the sum from 3 onward. This is the sum from 2 onward. This is the sum from 1 onward. I have fn x to the n plus 1. What should I pull out from this quantity? This looks a lot like g of x. G of x is the sum of fn x to the n. I have fn x to the n plus 1. What should I pull out of each term? I should pull out an x. And what should I pull out over here? An x squared. And so when I do that, this is almost g, this is almost g, this is almost g. They differ from g by not having, in this case, the first term, and this term is missing the first and the second. Well, let's just add and subtract. So if I add and subtract those terms, I get g of x minus f1 minus f2, x squared is x, g of x minus f1 of x. I've got g of x on both sides. I can solve for g of x. So I get g of x is x over 1 minus x squared. I have an explicit form for the generating function. And the idea is to now use this explicit form. One thing we could do is we could try to use the geometric series and expand things out. And we could say this is x divided by 1 minus x plus x squared. If we try to expand that out, however, we have a problem because x and x squared have different degrees. And you would have a nightmare of cross terms. Fortunately, there is a better way, and it allows me to review the least favorite of your calculus techniques. Have I asked you this question yet this semester? What your least favorite calculus technique of integration is? What is your least favorite? Partial fractions. So we do a partial fraction expansion. And if we do a partial fraction expansion, now we have 2 linear factors, and when I use the geometric series, everything is nice. And you will end up getting Benet's formula. So this can be used to solve a variety of problems, not just Fibonacci's, and it gives us a closed form solution. I can jump to the billionth Fibonacci number if I want. All right, so generating functions are wonderful. Depending on how the semester goes, we may see them later again, but for a lot of problems in sequel classes to this, you will use generating functions to prove a lot of things in probability. Here's a nice example. Let's say I looked at fn divided by 3 to the n. Well, because I know my generating function, this is just evaluating my generating function at 1/3. So your fraction 1 over 99,899 or whatever I gave you, that was just evaluating the generating function, the Fibonacci's, I think at like 1 over 1,000. And if you put in, not 3, but if you put in 1,000, what it's going to do is you'll get f0, then you'll get f1 over 1,000 squared, then f2 over 1,000 cubed. And in the beginning, they're going to be well separated and they won't interact. And that's why you'll get that beautiful fraction giving you all those Fibonacci numbers. And as you start to go far enough around, your Fibonacci numbers now have so many digits, they start to interact with each other. All right, so let's do an application. Let's do roulette. Just to be clear, the method I'm about to show you does not work. Do not use it. Do not go to Vegas or Atlantic City or any other casino and use it. If you do and you win, then of course forget what I just said and come back and remember. Okay? I am going to simplify roulette. How many of you have never seen roulette before? Right. We are going to do a simplified version where there are no green squares. Everything is either red or black. Right. This is actually bad for Vegas. They have an advantage because there's 2 greens, the 0 and the 00. So there's a 50% chance that you'll get a red number and a 50% chance you'll get a black number. Right? Vegas does not like to give you 50-50 chances, but it's fine. So there are many different ways you can bet. We will do very simplified betting. You bet either on red or on black. Right? And here is a possible strategy. It's called double plus 1. Bet $1 on red. If red comes up, you win $1. Great. If not, you are down $1. So bet $2 now on red. You lost $1. If you win, you just gain $2, so you now net $1. If you lose, you're down $3. How much should you bet? Nope.
Why not?
$4. So if you bet $4, if it comes up red, you've lost 3, you just won 4, now you're up $1. If not, you're down 7. If you lose, how much do you bet on the next time? 8. So this is why it's called double plus 1. You double your bet every time, and you will eventually be plus 1. And then lather, rinse, repeat, the shampoo instructions. Keep doing this until you win as much money as you want. There must be something wrong with this. I love teaching, but I don't love teaching this much. Right? There's a reason I'm not in Vegas doing this. Right? So there's a couple of unreasonable assumptions maybe about our model. Can anybody think of some issues of concern? Yes?
If you lose enough times, you're going to run out of money.
So there is the possibility that you will run out of money. Right? At some point, you might need to put down $1.4 billion. And if you lose that, you have to put down maybe about $2.8 billion. So how many of you have taken an economics class? Okay, so you are used to this stuff. So we will make some unreasonable assumptions now. It's called the eccentric rich aunt-uncle hypothesis. Okay, you have this eccentric rich family member who will back you with whatever financial reserves you need. They won't give you any money directly. They think that's wrong and they think you should earn your living. But if you need $2.8 billion, they will provide $2.8 billion for you. And if you lose and then you need $5.6 billion, they're there for you. And when you win the dollar, you don't have to give the dollar back to your aunt or uncle. Okay? I think we all agree that this is a very unreasonable assumption. If I can't even win in this case, the strategy has issues. There is another issue, and for this you need to know a little bit more of how Vegas works. So this one is harder.
Casino may not let you bet that much.
The casino doesn't have to take bets. So the casino will have a minimum bet at each table and a maximum bet. And they calculate these very carefully. Vegas really understands mathematics. They also understand facial software recognition programs. And so there are some people who can count cards. And Vegas knows who a lot of these people are. And they are extremely friendly. If they see one of them in their casino, they will actually have a private conversation with them in a separate room where they won't be bothered. There's a lot of really good movies and things we can talk about if you are interested in gambling and stuff like this. But there is a maximum bet. So the problem with this is you have to be able to place huge amounts of money, and Vegas doesn't have to take the bet. Sometimes on really big bets, what the casinos will do is they will call each other, and each one will put up a certain amount. But other times they will just refuse. So for this one, if you look at what's going on, well, after 20 bets, we're at over $1 million needing to be placed. So if we get 20 blacks in a row, we're in huge trouble. So I talked about the eccentric rich aunt-uncle hypothesis. The real issue is table limits. What if you could only bid $200? If you could only bid $200, we can only do it 7 times. Once we get to the 8th, we'd have to put down 256, and Vegas doesn't allow us. What happens is when you win small. You win $1. When you lose bad. Okay? This is all probability. I remember when I was young, my father wrote a computer program, I think BASIC, to just simulate this strategy, because he'd heard about this. He was wondering, damn, why aren't people doing this? And then he just saw how often he went bust. And so this is one of the reasons why I was able to go to college, is he ran the simulations before going to Vegas. All right. So let's let Pn be the probability we will not get 5 consecutive blacks and n spins. And then we'll let Qn be the probability that we will get 5 consecutive blacks and n spins. It's often easier to calculate the probability that something doesn't happen than to calculate the probability that something does happen. So this is one of the big ideas. And it turns out one of them is easier to calculate than the other. It's easier to calculate the probability we do not get 5 consecutive blacks. And then if we do that, then we can easily calculate the probability we do get 5 consecutive blacks. And I'm going to just assume for now that if we get 5 consecutive blacks, that bankrupts us, that wipes out our reserve. If you want to do 8 or 12 instead, you can modify this. And what I want to show you is the Fibonacci's that we studied, a close cousin of them comes in here. All right, so the resolution is not so great here. There is a video that I made with some students through OIT several years ago that I will post that does this a lot better. So we start off at with n spins to go. And we bet, and we have a 50-50 chance that we get a black or a red. Okay? If we start off with a red, how many spins are left? How many spins are left? Not 5. How many spins? N minus 1. Right? We're spinning n times. And we want to calculate what's the probability we don't have 5 consecutive blacks in n minus 1 spins. We've done 1 spin now. How many spins are left? N minus 1. Could this start off a string of 5 consecutive blacks? No, it's a red. What's the probability we do not have 5 consecutive blacks in n minus 1 spins? Pn minus 1. Could this start off a string of 5 consecutive blacks? Yes. So we have to analyze that a little bit more carefully. So this one will just be Pn minus 1, and this one now we spin again. And now 50-50. Could this start off 5 consecutive blacks? No. How many spins are left here? N minus 2, so that would just be Pn minus 2. And we just go all the way down. And at this point now, the resolution is fine. Do I have to worry about breaking this one up further? No. If my first 5 spins are black, what's the probability I don't have 5 consecutive spins? 0. That's why this is much easier, because now the recurrence relation stops. And it's going to have just a depth of length 5. If you allowed the double, the 0, the double 0, the greens, you would just make this number a little bit less than a half. Now, one of the things that's really nice is Vegas understands human psychology. And what they will do now is they will actually display the results of the last couple of spins in the roulette wheel. Because you can basically split a lot of morons into 2 categories. There are those who go, oh, red's come up 6 times in a row, red is hot, I should bet on red. And what's the other type of moron? Can't happen again, black is due, I should bet on black. They really don't care which category of moron you're in. As long as you are the category of moron with money willing to place the money on the wheel, they are happy. The more people that bet, the odds of them winning become very, very high. They just want to get you playing. So they will display stuff like this to excite people. 10 straight reds. 11 straight reds. Oh, Cuddy, we got to go in. We've got to go all in. No. All right. So it's just a 0 from this point onward. So we can start getting the recurrence relation. What's Pn, the probability we do not have 5 consecutive blacks in n spins? Well, it's 1/2 Pn minus 1, because that's the probability we got here. What's the probability we end up here? 1/4. And then and all the way up to 1/2 to the 5th. And so the initial conditions, what's the probability you do not have 5 consecutive blacks if you spin 0 times? 1, 100%. These are the easiest problems I can ask you all semester. If you only spin once, what is the probability you do not have 5 consecutive blacks? You only spin once, can you have 5 consecutive blacks? No. So the probability you don't have 5 consecutive blacks is 1. In fact, it goes all the way up to P4. So we have our initial conditions. P0 equals P1 equals P2 equals P3 equals P4 equals 1. And now we can use our recurrence relation and just march down and calculate everything. You could also use Mathematica and try to do things as before. It's a quintic. For those of you who've taken abstract algebra, you cannot write down, unfortunately, the roots in general as a function of the coefficients, but you can numerically approximate. We can, of course, write a very simple code and then just run the code. This is the probability that you will not have 5 consecutive blacks in n tosses with a fair toss or a fair spin. And I said if you had 100, if you do it 100 times, it's going to be about 80%. At 200, it's 96.59%. So the probability that you have bad luck at some point is quite high the more times you do it. And this is why this is a horrible strategy. But what if you are willing to risk losing a huge amount for the chance of winning a small amount? So much of math comes down to what question you want to ask. How many of you know about the tie between Clinton and Obama in the Democratic primary in Syracuse in 2008? This made the national news. I was applying for a position at Williams at the time, and I was looking at some other schools, and I actually got this as an interview question at dinner. Wow, it's amazing that they tied. No. There's so many places, there are so many cities in the country, you would expect to have ties somewhere. What are they going to report in the news? And in the news today, we did not have a tie in the following places. You report the thing that's anomalous. You report the thing that looks strange. Well, with the number of cities that were voting, you would expect to have some ties. And depending on how you do the modeling, the probability of a tie in Syracuse was somewhere between 1 in 1,000 and 1 in a million, depending on which assumptions you make. So depending on your assumptions, it wasn't that unreasonable. But it's the unusual events that will get the press. Over here, I could be asking, if I keep playing this long term, I'm dead. What if I decide to only play, say, 50 spins, and I'll accept whatever happens after 50 spins? What's the probability that I'm up after 50? Now, probably overall, more people are down than up. But what's the probability that an individual person is up? So you could ask, what is your likelihood of having won some money? So this is a great example of what we can do with the techniques of this class. This is a really simple modeling problem. In this case, we were fortunate that we could actually solve it theoretically. You can also write some code to simulate things. I'm not going to go into the description here. But this is the power of what we are doing. If you can solve it, solve it. If not, simulate it. Write some code, gather some data, and quickly convince yourself this is a bad strategy. All right, so we have about 5 minutes left. So since we talked about Fibonacci numbers, I thought I would just end with some fun, interesting properties of the Fibonacci numbers. Yes?
Just to clarify, I'm confused of exactly the strategy. Was the strategy just
so
to
the
waste
strategy,
money?
No. The strategy is to bet, and then if you've lost a certain amount of money, you bet that amount that you've lost plus $1 on the next time.
Okay.
And it doesn't matter if you bet on red or black either time, because we're assuming the two options are 50-50. So just keep betting, and then eventually you will win. The probability that you lose every single time goes to 0 as we do more and more spins. The problem is you have the house maximum, and so you can't recover your losses. There are things you could do to try to slow down and give yourself a few more spins, but all of these will fail in the end. It just grows too rapidly. Any other questions? All right, so I wanted to show you another way of looking at the Fibonacci's. This is just a fun aside as long as we've introduced them. So the first few Fibonacci's are 1, 2, 3, 4, 5, etc., etc., etc. It turns out every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. So one of the reasons I'm talking about stuff like this is I've had small groups over the past couple of years study things related to Fibonacci numbers. And one of the things I want to do this semester is give you some sense of what kind of research projects are you capable of doing at Williams after taking a class like this. So there's a lot of ways to prove this. One way is the greedy algorithm. How many of you have heard of the greedy algorithm from CS? At each moment in time, you do what is locally best. It turns out that is not always globally best. And at this time, I'll give you an example where what's locally best is not globally best. So I take 51, and I look at the largest Fibonacci number less than or equal to 51, which is Big Papi's number 34. So I get 34 plus 17. Now, what's the largest Fibonacci number less than or equal to 17? It's 13. And then I'm left with F8 plus F6 plus 4. So the largest one there is 3, and then 1. And if any of these numbers were ever adjacent, well, then I could have thrown away their sum, and then that would violate the previous number was the largest Fibonacci number I could throw away. So this gives you that a decomposition always exists. It doesn't show that it's unique. I'll leave that as an exercise. Here's the interesting observation. I first learned of this from Carl Pomerantz. I think he learned of this from George Andrews. If I take my Fibonacci decomposition, F8 plus F6 plus F3 plus F1, and I shift each index forward by 1, F9, F7, F4, F2, I get 51 goes to 83. 51 miles is about 82.1 kilometers. What's the conversion factor between miles and kilometers approximately? 1.6. What is the golden mean approximately? 1.6. Each Fibonacci number is approximately the golden mean more than the previous. If you are driving to Canada or in Canada and you are really bored and you want to stay awake because you're falling asleep, you can convert miles per hour to kilometers per hour by writing down the Zeckendorf decomposition and shifting the index. It is probably the worst application Now somebody wants to me, well, what if you have a small number like 12 and you want to convert? It doesn't do so well for small values. Do you know how you would do a number like 12? Take the number 120, convert 120, and then divide by 10. So if it's better in the limit, just add a couple of zeros. So it turns out you could ask questions such as, how many summons do you have in a typical decomposition? So if I choose a number at random and I count how many summons, it turns out it's normally distributed. And so a couple of small students proved this, and they generalized this. Key input in the generalization was looking at these generating functions. There's a lot of questions you can ask related to this. Just as a theoretical aside, how many of you have never seen the Fibonacci numbers before today? Everyone has seen the Fibonacci numbers at some point in their classes? And you've always seen it defined as each one is the sum of the previous two. It turns out you can define the Fibonacci's as the unique sequence such that every integer can be written uniquely as a sum of non-adjacent terms. So I start off with 1. I have to add 2. I can't do 1 plus 2 because they're adjacent, so I have to add 3. Can I make the number 4? Yeah, how can I write 4 as a non-adjacent sum? 3 plus 1. So I don't have to add 4. Can I get 5 as a sum of non-adjacent terms? I have to add 5. Can I get 6? Yeah. Can I get 7? Yes. Can I get 8? So the next number I have to add is 8. Can I get 9? Yes, I can get 9. I can get 10. I can get 11. I can even get 12. I can't get 13. It turns out this is an equivalent definition of the Fibonacci's. And then you can ask questions, if I give you decomposition rules, what sequence is related to that? And so there's a lot of stuff you can do here. I've done a lot of work with this with my students. There's central limit theorems looking around. I really don't want to go into details. This way you can just hit pause. But what I want to do is I want to end with looking at gaps. So if I have a sequence of summons in a decomposition, I can ask, how long do I have to wait before summons? What's the probability I have to wait 1 unit, 2 units, 3 units, 4 units? Well, since I can't have adjacent terms, I can't have a gap of size 1. All the gaps have to be at least of size 2. You end up getting that there's a nice geometric decay. And so the probability of having a gap of length k converges to 1 over the golden mean to the k. And the reason I wanted to end on this was just talking about how you display information. When you look at this, you might think that this is geometric, but this requires a little bit more of a knowledge of how these probability distributions look. What I'm plotting here is I'm plotting the ratio of each probability to the next probability. And if it's geometric, then all those ratios should be about the same. And you can see here that up to a good amount of time, yeah, those ratios are looking about the same. We're going to talk a lot as the semester progresses about what is the best way to present information. So I just want to end with one example of where what is globally best is different from what is locally best. It's from a great series of papers, Do Dogs Know Calculus? So imagine you have a dog here and you throw a stick here. How should the dog swim? How should the dog move to get to the stick? Straight line. I throw the stick over here. Straight line. I throw the stick over here. How should the dog go? No, the dog knows calculus. And this actually dog, his name was Elvis. They have videos of this. He knows to swim diagonally to shore, run along shore, and then come back up. Why? The dog goes faster on land than in sea. If you want to say locally, the best thing I could do to minimize my distance is to move straight forward. But globally, that's not best. Globally, it's actually better to take a little bit of a sack in the beginnings. And again, these are things you really need to be aware of. Sometimes a method will give you a decent solution, but will not give you the best solution. All right, this is a good place to stop for today. We will do these.